Hello, everyone. Welcome to PyData Global 2021. I'm Florian, and I'll be the host for this session. And I'm delighted to have with me Reshama and Nidhin to talk about deploying a mobile app on TensorFlow lessons learned. Reshama is a statistician and data scientist based in New York. She's a founder of Data Umbrella, a community for underrepresented persons in data science. She's also a Triage Team member of scikit-learn and an organizer for the New York chapter of PyLadies. Nidhin is a senior machine learning engineer at Walmart Labs. With this, I'll hand over to both of you for the presentation. Looking forward to it.
Okay, welcome to our presentation, Deploying a Deep Learning Model on Web and Mobile using TensorFlow, JavaScript, and React Native. And this is sort of an overview of our journey through that. My co-author on this project is Nidhin Pattaniyil, and you can find Nidhin on Twitter and GitHub at npatta01. And I am, you can find me at Reshama S on Twitter, GitHub, and LinkedIn. So I'm going to go over the outline of our presentation. I'm going to go over the data set that we used, and then I'm just going to show a brief short demo of the web and mobile app. I'm going to go over some computer vision concepts, and also we're going to be going deploying on web and mobile. So the data set that we used is data from the foodspotting.com website, and it's 101 of the top food categories, and it's 1,000 images per class. And this data set is also available on Kaggle and TensorFlow datasets. So this is just a brief GIF of our web app, and there's options to either upload an image or take a URL, and it gives a prediction of the top 5 possible with predicted probability. Our source code is available on GitHub at Reshama/deploying web app, and the Heroku app link is over here. And this is just a GIF of our demo app, web demo mobile app. And there's an option to do a camera or a upload an image or take a picture, and it gives the top 3 predictions. Now I'm just going to go over a couple of computer vision concepts. So we used a convolution neural network. We use deep learning because we're working with an image data set. And since 2012, convolution neural networks have become the standard after the well-known famous ImageNet competition. And CNNs are composed of convolutional neural networks with max pooling operations. So I'm going to show here a baseline performance of architectures, and this is based, these are benchmark numbers, and they're based on the ImageNet data set. They're also based on the web, not mobile. And we worked with a few family of architectures. There's VGG19, ResNet50, and MobileNet v2. And we can see that, VGG19, the size of the model file is quite big, 549, and MobileNet v2 is used for mobile web deployment, and we can see that it is much smaller at 14 megabytes. We can see that despite which family of architectures we use, the accuracy is similar. And this represents the parameters in the model, which are correlated with the size. And we can see as for MobileNet v2, the number of parameters in the model is 3.5 million, which is much, much lower than 144 million. This right here gives the inference time on CPU. And we can see also that as we use MobileNet, it is much faster on MobileNet v2. And for the CPU, it uses a pretty powerful machine, 92 core. And the inference time on GPU, we can see it's also faster for MobileNet v2 versus ResNet50 VGG19. And just to note that this is based on a pretty powerful GPU. It's a Tesla A100. So we use model optimization, and the reason is that the 14 megabytes is much smaller than other, but it is a bit too large for mobile deployment. And so what we do is we optimize the model. And we optimize the model, so we reduce the size, and reducing the size of the model has all these downstream effects, which are favorable. It takes less storage space. It's faster to transfer the model. It has a smaller download size, so it uses less memory, and it takes advantage of the hardware on our devices. Quantization is it's a conversion technique where we work with the model size, and it reduces the model size without much of a loss in model accuracy. And thus we can, we have comparable accuracy, we can save time, and we can save memory. And so these numbers right here are also benchmark numbers, and they are based on the ImageNet data set. And it's on a Pixel 2 phone. And we can see that MobileNet V2 for the inference time is about 90 milliseconds. And after it's been quantized, it goes down to 54 milliseconds. The model size is about half. And we can see that the change in accuracy is not very different. Okay, and with that, I'm going to hand this over to Nidhin.
Cool. So thanks, Reshama. So, now we have our optimized model, right? So now we want to actually make our model available for our users. So, the most obvious way to do that is to deploy the model as a service. Right. So in Python land, we have some very great web frameworks, like we have Flask, we have FastAPI, we have Django. But one of the problems with these web servers is that they're not really optimized for model serving. So one popular model serving, especially for TensorFlow, is TensorFlow serving from Google. So it's optimized for model serving because it can serve multiple models. It supports like micro batching requests. So especially if you are using an accelerator like a GPU, if you have like 50 requests coming per second, you can have all these requests automatically concatenated and fed to a GPU. So kind of better utilizing the hardware. And especially in production, you want to get like these model metrics captured. So TensorFlow serving has all these options. So especially for production, this might be one way of deploying. But in our case, this is just kind of like a hobby project of ours. And we also wanted to have like a interactive front end. So we decided to just go with FastAPI. So, that's deploying on the server, but, there's actually been recently a new deployment option too, and that's deploying on the browser with TensorFlow.js. So TensorFlow.js is a JavaScript machine learning library from Google that runs completely on the browser. So, you can take an existing Keras or TensorFlow model, you can port it over to TensorFlow.js, and you can even actually train new models on the browser itself. It supports multiple platforms / backends, so you can run inference just on the CPU. It can also utilize WebGL and WebGPU, so that means it will actually take advantage of the GPU that might exist on your machine in the browser. It also supports like Node.js, so it can actually run JavaScript server side, and it also supports React Native. And the beauty of going this route is once the model assets are downloaded locally by the browser, inference runs completely locally. There's no server or whatnot. So, TensorFlow.js seems exciting. Let's look into what it takes into converting the model to use this, and some considerations to think about. So one thing is, we went from a 14 megabyte model to a 7 megabyte model artifact, but this binary file size is still a little bit large. It's not really mobile. It's not really browser friendly, right? So what you normally would want to do on the browser is to have maybe small files, maybe less than 1 megabyte or so that the browser can download all these files in parallel, and also like you don't hit any browser cache size limit. And so here we set a really large value for the weight shard size of 50 megabytes. But we just use this because later, since we're going to be deploying it as a mobile app, we just wanted to have one shard. So that's why we just put a very large value, but it's not really recommended if you're just planning to deploy on the browser. So the next thing to think about is, the model that we trained and we exported, from Keras, it's an H5 file. Is that the model can be later reused for training, right? But if you're only going to be using it for inference, there's a lot of layers inside the model that are not really optimized for that. So especially if you're just using for inference, what you can do is, you can drop some of these layers, so you can fuse some of these layers. So the conversion script that we're going to use is basically going to create this graph, analyze it, and then, drop or combine these layers. The other thing that we can do with the script, is apply quantization, as Reshama mentioned. So, normally you might go from 32-bit precision to 16-bit precision, and you can even go down to int 8, which is if the accuracy works for your use case. And the script allows you to quantize, just some layers by layer types, or at a certain level deep in the model. So let's see how all these things play together. So here's the script TensorFlow.js Converter, which you can install from pip. And here you see all the things that we mentioned. We have a Keras H5 model. We output it to a graph model. We asked it to export it to basically one shot. We apply float 16 quantization, and then we export it. So, great. We have our TensorFlow.js artifact. Now we can load it in the browser. We can build a nice UI with our favorite JavaScript library of choice. But, maybe there may be a scenario where, the browser might not be the ideal thing, right? It might be very difficult for a user to always be in front of a computer. So maybe you want to make it more accessible to your users. So mobile might seem like a good option. So, globally, people have been spending more time on their mobile devices, and I can definitely say that is true for me too. And, so you do want to, especially if this is an application that you think might be useful for your users, you should try to make sure that it's more accessible to your users. So it might be useful to consider mobile inference. And there are other benefits for mobile inference too, right? So if the inference is running on your phone, then you don't need any internet connection, right? And if you don't need an internet connection, that means you're also not sending, users messages or users images to a server, right? So you're protecting their privacy. And also, because there's not all this bandwidth for sending the payload to a server, the latency can actually be lower, right? So I hope you can see, there are possibly a lot of benefits from mobile inference. So let's see, what are the benefits of action, or how do we actually get there? So, if you're targeting only iPhone users, there is CoreML from Apple, right? So, and you have to use, you have to write a Swift app, right? Because that's what iOS and apps are written in. If you want to target both Android and iOS, Google has TensorFlow Lite, which you can target both platforms, but you need to write separate code bases, right? There's a Swift app for iOS, and then there's a Java app for Android. But last year, there's been really a new option, the React Native adapter for TensorFlow.js. So we saw TensorFlow.js can be used on the browser. It could be used on the server for Node.js, and now it can also be used with React Native, right? So React Native is a cross-platform mobile development framework. So you just write in JavaScript, and there are bindings for native iOS and Android views. So you can take advantage of basically just one code base. So another reason why you might consider using JavaScript is, according to Stack Overflow, JavaScript is a widely used language. So there are a lot of resources that you can use. So for our use case, we decided to go with TensorFlow.js React Native because we were more comfortable with JavaScript. And if you look at the chart here, the Swift user base is pretty low, right? It's only used for mainly iOS developments. So yeah, we decided to go with TensorFlow.js. And like, what is the code to actually use this? So since we're using React Native and TensorFlow.js, like this code that you see here is the same code that's used in the browser and also in the mobile app. So in the first 3 lines, we're just basically loading the model. We're basically loading the model artifact. And line 3, you're just basically loading a mapping from your model output to like a friendlier name. And then in line 5, you just basically load the model, the graph model. In line 6 is you just basically feed a tensor in. So this looks pretty easy, right? It's JavaScript, but it looks pretty familiar. The APIs look clean. So maybe other than the ease of use of maybe React Native, is there any other benefits of maybe going this route? So, React Native, and I would say technically Expo, there's a lot of tooling that's built for this environment, right? So, so not only do you only need to develop once, but if you want help or to deal with the whole process of deploying to the App Store and whatnot, Expo can actually do all that management of managing your secrets, building the binaries, and also because of the way how Expo and React Native is, where it's basically JavaScript code, depending on the types of updates you make to your application, you can actually update your source code and export your app updates to Expo, and you can actually have your users instantly getting updates to your app outside of the usual Android and iOS release process of publishing binary. Cool. So now let's get to the demo stage here. So let's just hit this the web app demo, and we'll later show the mobile demo also. So let me just reload this page. So as Reshama showed earlier, you can select one of the URLs to upload your own URL. And on the left-hand side, we will be doing inference where we're calling the server that's on Heroku, like the FastAPI backend. And on the right-hand side, you will see inference actually running with TensorFlow.js. So, let's see which one is faster, right? So, for this image, we basically get about the same classes with about the same confidence. We see the inference time on the server is 300 milliseconds, about 300 milliseconds, but the whole total time was about 853 milliseconds. On the browser side, we see that it's about 179 milliseconds, and there's not really much other time because most of the time the image is already loaded in the browser, and so the inference just happens. Let me just run predict again because probably the model needed to be loaded on the server the first time. Maybe there may need to be some setup action that happened on the browser. So now we see that the inference time is 42 milliseconds, but there's still a little bit of instability again on the server side. Let me just run it again. Yeah, we see like the clients, the inference on the browser is about stabilizing, like let's say 40 or 50 milliseconds. I would say 40 to 50 milliseconds is wonderful for the browser. So why did we see like a large time in the beginning? In the beginning, because TensorFlow.js is kind of binding to like WebGL to kind of use the GPU, and so like the first time it needs to initialize like the mapping to the WebGL shader programs. So that's why it took some time, but after the first compilation of that, it can just reuse those assets. So that's why we see such a fast time here. Yeah, one thing to mention on the server side here, this is the model without any optimizations. So, an optimized model can run in a pretty fast manner in the browser. So the next thing is I want to show you it also on mobile. So let me take my phone here. So here I am casting my Android Pixel 4a phone. Let me open the Expo app. So this is the mobile version of our app. And let's choose an image. So let me just choose this KCDA image. And we see the inference here. So this is React Native running TensorFlow.js. So the total time was about 340 milliseconds, but the prediction time was about 60 milliseconds. So kind of let's look into this a little bit, this inference time a little bit more. So let me just move this away and let's go to the slides. So on the desktop browser, we saw we're able to get 40 milliseconds. I didn't show the mobile browser, but if you run the inference, you get about 175 milliseconds. And as we saw in React Native, the inference time was about like 50 milliseconds. So, I think these are acceptable numbers, but maybe if you want to have, better for your application, if you maybe need better numbers, let's see what options we have. So if you really do want better numbers, you might want to consider TensorFlow Lite. So in the first column, we have just CPU-based inference using 16-bit quantization. So we see over the years, if you just look at Google's flagship kind of phone, we see CPU inference has definitely gotten better over the years. And obviously, if you can quantize to ints, you can see that we're getting all the way from 80 to 22 milliseconds, which is great. But if you look at the right-hand side, we have something called neural network API. So both Apple and Google has, like custom chips that they have on their phones. So if you use TensorFlow Lite, you can use, it has adapters to use some of these accelerated APIs. And if you look at this, like in the beginning, the first versions was not really good. It was even slower than the CPU. But if you look at like the results for Google Pixel 6, the latest model, we're getting all the way down to 2 milliseconds. And if you can quantize to ints, that's 1.5 milliseconds. I would say these numbers are really amazing, right? Like if you remember before when we looked at the Tesla A100 numbers that Reshama showed, we were getting like about 4 milliseconds on a server-side GPU. But here, we have that same mobile-friendly model, but quantizing it and taking advantage of the hardware, and we're getting really great numbers. So kind of just closing out some things and some takeaways. They are, it's not always enough like to go after like maybe like the newest and latest models, right? They're not really optimized for mobile. And if that's a use case that you want to consider, do consider these if mobile efficient models like MobileNet. They're actually newer version. There's actually a newer version of MobileNet V2. MobileNet, we used V2, but there's a V3. And there's another family of architectures called EfficientNet Lite, which give about the same accuracy, a little bit better, but the efficiency is even much better. And like running inference on the browser on the phone is doable, right? And you can use TensorFlow.js and a React Native adapter to get pretty good performance, I would say. But if you really, really want the best thing, you should consider using TensorFlow Lite or Core ML to use like the GPU accelerators and advanced chips. So if you found this stuff kind of useful, like Reshama and I have a course that we created with Manny that kind of walks you through some of these deployment methods and some of these information. You can also read about the stuff that we presented at this Medium blog, and you can again find the links to our code in the 2 repos here. And that's about it. If guys have any questions, definitely would love to help answer them.
Thank you so much. Great talk there. So far, I haven't seen any question, but everybody in the audience, feel free to kind of post your questions now. I would have one. I remember I deployed kind of a computer vision model on the kind of the little Raspberry Pi type of, but the Jetson Nano as well. So I had like some challenges. So I'm just curious, what was the kind of biggest challenge that you were facing when you did the deployment on kind of mobile browser? What was the kind of nitty-gritty thing that you didn't expect at the beginning that ate up some time?
Sure, I can take that. So I would definitely say, like the Python TensorFlow library is very well maintained, and TensorFlow.js, it's a little bit newer. It's also kind of well maintained, but like the React Native adapter, it's like, it seemed, to be honest, like a little bit spun off project a little bit, and maybe because it's just newer. So, like dealing with compatibility with the Python model, with TensorFlow.js, and then TensorFlow.js React Native adapter, like we had to get the versions kind of right, because they definitely didn't make it easy. So like when we played with it, we couldn't directly use things from TensorFlow Hub because the conversion from Python to TensorFlow.js, it didn't support like the hub layers. So I would say that was one of the biggest things, like just dealing with the versions. Again, for our case, luckily we were just using on a browser and the phone, which has a little bit more compute than like the edge devices. But it was kind of, I guess, enlightening and a little bit sad to see that the big difference, right? If you really wanted to get the best performance, you should use like, TensorFlow Lite. You can get 2 milliseconds versus like the 20 or 40 milliseconds. So.
Great, thank you so much. Yeah, version problems. I feel the pain. All right. I don't think we have any further question at this point. Let me thank you again for the great talk, and I hope you enjoy the rest of the conference. Thanks everybody in the audience as well. And yeah, have a great conference.
Thanks.